Okay, let's continue our conversation about imaginary numbers. So I should entitle this maybe more about imaginary numbers because we did get started. Imaginary numbers are not real numbers, okay? So we keep talking about these things that are real numbers, and now we have finally the things that are not real. We call them imaginary. We learned the definition was really that I was defined as, so we can use a triple dash, that's defined as the square root of a -1, which means I squared is equal to -1. And this turns out to be the more useful thing to remember. Okay, whenever you run into that I squared, you're going to call it a -1. Okay, so what are some of the things we didn't talk about yet? Well, what happens when you have greater powers of I squared? So we started this with I is the square root of -1, I squared is -1. What's I cubed? I cubed, well, did you think about it? You're certainly going to be able to break it down into I times I squared, which would further break down into I times -1, because remember, every time we see an I squared, we change it into a -1. And so I could just write that then as minus I. So really what I have is I cubed is equal to a -I. Okay, I can do the same kind of thing for I to the 4th. Let's work that out over here. And I could split that up however you like. I'm going to choose I squared times I squared. So each one of those is a -1 times a -1, and you get +1. So down here I'd have to put I to the 4th is equal to +1. And we could keep going. Let's try I to the 5th power. How would you break that down? One way to break it down would be I to the 5th is equal to I to the 4th times I. And we know I to the 4th is just 1 times I. So I to the 5th is equal to I. And you can kind of see now we're back to where we started, which was up here, just I. And so we're going to repeat this process over and over and over again. There's a cool trick for predicting what is I to the 457, or any number at all. I just made 457 up. There's a nice trick to that, and it works for anything that has a pattern like this does. So I want you to think about the pattern of the I's with the exponents, and think if you can come up with a rule that would work for how to predict what I to the 457 is. This is a wonderful SAT type of question that you really do get quite a bit on those. So I'm going to let you play with that for a while. Okay, why do we use imaginary numbers? Well, let me just show you one thing. If you had x squared plus 36 was equal to 0, we would have said this is a unfactorable. I can't solve it by factoring, so I'm a little bit lost. So let me show you another method to solve this. We have this method called extracting square roots, where you're trying to take a square root of both sides. So x squared would equal -36, because the idea is you have to isolate the x square, okay, so that then you can take a square root. Okay, so if I do that to this problem, take a square root of both sides of that equation, on the left I'll get an x. Technically I get the absolute value of x. We'll work on that. And on the right hand side you're going to get a plus or minus. And that's because we didn't write the left hand side as an absolute value. So maybe I'll explain that in class tomorrow. But the point we're trying to do today is this square root of a -36, and of course that's going to be 6i now that we know how to take the negative out as the I, and then you're left with the square root of 36 as the 6. Alright, so now I'm able to solve what was otherwise unsolvable over the real numbers. We can now solve it using complex or imaginary numbers. So first of all, I slipped there and I said the word complex number rather than imaginary, so let me explain that. A complex number consists of a real plus an imaginary part. Okay? So in general, a complex number is A plus BI. So you have this is your real part, and B is the coefficient in the imaginary part. Okay? And this is a standard form, so you're going to hear me quite often say all your answers have to be in this standard form. So yes, I am nitpicky about that. All the answers must look like this form. So let me show you what we do with this. Okay, one of the things you can do is equate complex numbers, and you do that by you break it up. The real part has to equal the real part, and the imaginary part has to equal the imaginary part. So I would look at this and say, here's a real part, here's a real part. So I would say A is equal to 3. So I found A. And I'd look at the imaginary parts and say BI must equal negative 7I, therefore B must equal to a negative 7. So that's really not hard to do. It's one of those things, please don't make it harder than it really is. Okay, we can add and subtract with complex numbers. So again, you're going to add real parts with real parts and imaginary parts with imaginary parts. But this shouldn't be hard for us because it's just like imagining, that the little I for the complex number is really a variable like an x. So treat it like an x and you won't have any problems with it. So, I mean, simple things like, so I had 2 plus 3i minus, and let's do another complex number, 5 minus 7i. So what you're going to do is simply look at this and say 2 minus 5 is negative 3, 3i plus 7i makes a plus 10i. And there you have it, and it is already in, that's nice standard form for a complex number. So not too hard there, right? Okay, so of course we're going to want to know how we can multiply complex numbers. So that's not hard. It's just the only difference is you got to remember what to do with I squared when you get it. So remember, I squared is equal to a minus 1. That's going to be what we need. So let's try a problem. Let's say, and I'll even do it where they're both complex, 2 minus 5i. Let's say I want to take that times 3 plus 4i. Now, of course, this is going to be a FOIL situation because I'm multiplying two binomials. So we'll start with the FOIL. 2 times 3 is 6. Then I have minus 15i plus 8i. Oh, Lord. Minus 7i. That's one of those funny ones that Justine has a little mental block on, so I always have to think about that one. But I got it, I hope. Minus, and then I've got this 20 I squared for the last product. But, so normally I would be done if I had been an x and I squared, but of course now I have imaginary I squared means something, so I'm going to replace the I squared with the minus 1. So minus 20 times negative 1 right there. So I have 6 minus 7i plus 20. So now I can combine those like terms, 26 minus 7i. So there you have it. So the interesting thing is that you will never have higher powers, exponents with your imaginary letter. Alright, so that's as big as it gets. So that's multiplying. Okay, the deal with dividing is a little bit different, and the thing to remember is we have a rule that we have no i's in the denominator. Okay, it's just something that is not allowed. Okay, somebody wrote a rule, I don't know who it was, but we have to do this. So say you had what looks like a division problem in fraction form, 2i divided by, let's make something up, 2 minus 5i. Okay, so what are you going to do? I'm not allowed to have that I in bottom. Well, what we do is call multiply by, and it's both top and bottom, okay? Top and bottom, by what we call a complex conjugate. You've heard me use the word conjugate before, and that was when we changed the sign of the second number. And now we're going to change the sign of what for us is the second number is the imaginary part. So I'm going to take this 2 over 2 minus 5i, multiply top and bottom by 2 plus 5i. This is your complex conjugate, 2 plus 5i. So now all I have to do is multiply that together. Well, look what happens. This neat things are going to happen. On the top, it's a little bit boring, and honestly, it's probably better to leave it alone for now, because maybe you want to cancel things. So I'm going to leave the top alone. But on the bottom, very, very good things happen. Multiplying these, remember, these are conjugates of each other. And remember what happens when you multiply conjugates, you get a difference of squares, right? Those middle terms drop out. That's why we chose conjugates. Okay, so I'm going to do it out the long way just to prove it to you again. I get 4, I get minus 10i plus 10i, those cancel. And then I have minus 25i squared. So you say, oh, there's still i's in the denominator, but no, there isn't. So let's try this again. And I can see now the bottom's not going to give me anything nice to cancel. I'm going to go ahead and do the top. 4 plus 10i. And on the bottom, 4 minus 25, I'll go slow, the I squared turns into a minus 1. Remember that? That's the really important thing. So, keeping going, bring this on down. I have 4 plus 10i over 4 plus 25, so let me just go ahead and call that 29. Now, you might think we're done. There are no more i's in the denominator. But you have to ask yourself, is this in standard form for a complex number? And the answer is no. Because remember, that was supposed to look like a plus bi. But right now I've got this all over something. Now, a can be a fraction, and b can be a separate fraction, but they're separate numbers. So, what do you have to do? You have to change this to 4 over 29 plus 10 over 29 times I. And that is your answer for dividing this. So here's your trick, multiplying top and bottom by the complex conjugate. Alright, so I think you have some problems in the book to do for the check your understanding. If you have any questions, you can email me or please bring them up in class.